equals our first term times our common ratio raised to the n minus 1. That is our explicit. That is the one I can just plug information in and get it out. It also asks for our recursive. Recursive, just remember, you need two parts for recursive. You first have to state where your recursive starts. Does it start at 2, 3, 4, 5, or 6? So you do have to have an a sub 1 equals some number. Now, on top of that, we need to go, okay, a sub 1 equals x. Now we need our formula. And just a reminder, our formula is going to be the term I want equals the term before it multiplied by some number. So our explicit form is a sub n equals r times the term before it. You're just multiplying by r over and over and over. As a quick reminder, our recursive is based upon the number before it. So a recursive takes a while. If I ask for the 100th term, you have to come up with all 100 terms to get to it. Where explicit is our cyclic. So once again, that would be our recursive. You need both parts to be correct. All right, arithmetic is the one where we're adding, so we probably have adding in our explicit formula. Our explicit formula is going to be a sub n equals, once again, we start with our first term, but now we add versus multiplication. Well, we're adding n minus 1 times our common difference. I am going to note the explicit in the arithmetic and the geometric both have an n minus 1 in there. So it's important you remember that n minus 1. Don't make it n plus 1. Now you have the wrong formula, and you have a lot of stuff going wrong. All right, our recursive. Recursive is, once again, you do have to state where you start. And for recursive, it's the term I want equals the term before it plus a common difference. So the term I want would be a sub n. The term before it would be a sub n minus 1, and we are adding that common difference. Once again, the top one is my explicit, bottom one is my recursive. Questions on explicit and recursive formulas for arithmetic or geometric? Okay, then let's go over some information from the homework. All right, first and foremost, there's a couple of them that were covered up. Look like, what, number, nope, I have the wrong one, I think. No, we don't. Was it number 4 that was covered up? For those that asked to check their answer? All right, that one should have came out to negative 127.5. So number 4 should have been negative 127.5. The other covered up one was number 12. And number 12, the answer should have been 1. For number 12, the answer should have been 1. On number 13, there was a mistake on it. Several people got the point for it. It should have been negative 7.43, not a positive 7.43. It doesn't make sense that it would be a positive 7.43 because we had nothing but like that negative 9.9 on it. All right, going over those questions, what other questions do we have from that homework? Yeah, go ahead.
Could you go over 15?
Sure. So 15 was, we're doing a sum where I equals 1 to infinity. And we have 6 times 0.1 to the I. All right, so the first question is it arithmetic or geometric? It is geometric because it's exponential. Well, as soon as I determine it's geometric, then we determine is it infinite or finite? Well, it's infinite. So since it's infinite and geometric, we do have to get our common ratio, which is 0.1. And then we have to do that check. We have to make sure the absolute value of 0.1 is less than 1. It is. So we can actually find the sum. Now, just a reminder, our sum formula, if it's infinite, is first term divided by 1 minus r. So let's get our first term. Our first term is where I'm plugging 1 into the equation. So that'd be 6 times 0.1 to the first. Well, that'll be 6 times 0.1, which should result in 0.6. That means my sum is going to be my first term, which is 0.6, divided by 1 minus my r, which is 0.1. That will come out to like 0.6 repetant. I simplified it to 2 over 3, but I would have been fine with just that, 0.6, either repetant or 0.67 kind of thing. Okay? All right, other questions? Yeah? Number 4, we were supposed to get out, 127.5 in the negative fashion. So we're going to notice when we're doing the sum, it's a finite sequence. So that means I need my first term. So on number 4, our first term is that 1.5. It does turn out to be geometric, and it alternates between negative and positive. So we do have a negative 2 as our r value. And then we have 1, 2, 3, 4, 5, 6, 7, 8 terms. All right, plugging that into our sum formula. Our sum would equal our first term, which would be 1.5, times our 1 minus our r value raised to our nth value, all over 1 minus our r value. Did you have all that? Yeah. Okay. Then it was probably just a calculator error, because it should come out to negative 127.5. So just double check your parentheses. But the work itself is correct. Today's lesson is a little bit easier. A lot of it has to do with kind of common sense stuff. So consider it 6 a.m., you're groggy, but you have to pick out an outfit to wear. Lucky for you, you didn't do laundry and you only have 3 pairs of pants and 3 t-shirts to choose from. I'm going to make your life even easier. One of your shirts is stinky, so we're just going to say you only have 2 t-shirts. We don't need to go all the way to 3 t-shirts to choose from. How many outfits could you wear? Well, the first thing we're going to talk about is something called a tree diagram. A tree diagram might seem like it's just a building block, but sometimes a tree diagram can be the easiest way to solve a particular problem. There is one problem on the homework that a tree diagram is the easiest way to solve it. So a tree diagram is basically me drawing out every possibility. So we're going to do a tree diagram. Let's go over here. Tree diagram. I don't know. It's not writing. All right, our tree diagram is going to start with our first 2 choices. Let's pick our shirt first. We're going to say everything matches, so no worries there. We have 2 shirts to choose from. So that means I'm either going to pick shirt 1, shirt number 1, or I'm going to choose shirt number 2. So right off the bat, I have 2 choices. 2 different outfits I can make with shirts. Now, once I pick shirt 1, like I said, all 3 pants are awesome choices. They all match, so there's nothing. They all have equal chance of me picking them. So once I pick shirt 1, I now have 3 pants to choose from. So let's call this pant 1, pant 2, and pant 3. I assume I should put pants, but I like the pant 1, pant 2, pant 3. All right, now I went back in time, and I actually chose shirt 2. Well, shirt 2 also has 3 pants I can wear with it. So shirt 2 can branch off into pant number 1, pant number 2, and pant number 3. All of your possible choices are up there. I can wear shirt 1 with pant 1. That's one choice. Shirt 1, pants 2. Shirt 1, pants 3. Shirt 2, pants 1. Shirt 2, pants 2. Shirt 2, pants 3. So when we get to the end, this is how many choices we have. So at the end, we're going to have 1, 2, 3, 4, 5, 6 different choices. So there are 6 possible outfits. But I'm going to quickly notice something. There might have been an easier way than drawing this particular problem. And that is the fact that if I have 2 shirts and 3 pants, 2 times 3 is 6. That is not a coincidence. I could have got my answer by just doing 2 times 3. I have 2 choices to start off with. I have 3 choices for my second one. I can just do 2 times 3. So notice that each choice of pants leads to 3 shirts. We kind of flip that. So we have 2 choices of shirts. Or in other words, we can just do 2 times 3 or 3 times 2, which equals 6. 2 shirts times 3 pants equals 6 total possibilities. This is something called the fundamental counting theorem. The fundamental counting theorem. The fun, puts the fun in dementals. Fundamental counting theorem. All right, the exact words for the fundamental counting theorem is if you can choose one item from group M and a second item from group N, then the total number of 2 item choices is M times N. So if we threw in socks into our option, we have 2 shirts, 3 pants, maybe 5 pairs of socks. I'll just do 6 times 5 to get my next choice. Now if I add on, I don't know, a hat or something, we can just add that on. It's just how many choices you have on each one. Let's make sure we're doing the lesson, not the homework. We just keep adding on that multiplication. So it's not just 2 groups, it's an infinite number of groups. In fact, if we look at our next example, this is going to be a prime case for the fundamental counting theorem. So we have a phone number composed of 10 digits. The first 3 are the area code. And I'm going to note something here. The area code cannot start with 1 or 0. And the other 7 are our local phone number. Our local phone number cannot start with a 0. How many possible phone numbers are there? I will note this is true, but there's a whole lot more restrictions on telephone numbers. Like one I can think of off the top of my head is your phone number can't have 911 embedded in it. Can't be like 682-9113. Because back in the day when you had a landline, as soon as you typed in 911, it would call the cops. No matter if you typed in numbers before. And there's lots of little nuances with that as well. We're just going to do the very basic ones. So we cannot start with a 1 or a 0. So when I'm looking at my first number, my first phone number, how many numbers do I have to choose from? What was that? 8. We're going to have 8 to choose from because we lost 1 and 0. Normally we have 10 to choose from. We can go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, which would be 10 choices. But I'm eliminating 0 and 1, so I only have 8 to pick from. Well, the rest of my area code doesn't have any restrictions on, so I have 10 to choose from, 10 to choose from. I got 8 numbers to choose from, 10 numbers to choose from, 10 numbers to choose from. Then I get to my local number. My local number can't start with a 0. That's 1 I got to lose, so instead of 10, I only have 9 possible numbers that could go here. The rest, though, are 10s. So how is this the fundamental counting theorem? Well, what I'm actually dividing this up into is 10 individual groups where I'm pulling numbers from. And I need to pull 1 number from each of these groups. Just like where you had 2 pairs of pants, or 3 pairs of pants and 2 shirts. I have 8 numbers, 10 numbers, 10 numbers, 9 numbers, 10 numbers, 10 numbers, 10 numbers, 10 numbers. So if we have all of these groups, and I'm pulling 1 item, note I'm pulling 1 item from each group, we just need to multiply all the groups together, and we'll have our answer. So we're going to do, by the fundamental counting theorem, we're going to do 8 times 10 times 10 times 9 times 10 times 10 times 10 times 10 times 10 times 10. Now, you're most likely going to want to plug this in your calculator. You really don't need your calculator, though. Let's break this down a little bit. So we have 8 and 9. Let's think of 8 times 9. Now, the rest are tens. We have how many tens? We have 1, 2, 3, 4, 5, 6, 7, 8. So I'm multiplying by 10 to the 8th power. The only real multiplication you need to do is 8 times 9, which would be 72. When you multiply by 1 10, you add 1 0. When you multiply by 8 tens, you add 8 0. So we're going to have 72 followed by 8 zeros. 1, 2, 3, 4, 5, 6, 7, 8. 3, 3. So we're going to have 7,200,000,000 possible combinations. Sounds like a lot, but think about how many phone numbers are out there.
I mean, like in the U.S., right?
Right. This would work for the U.S. There is thought that we might run out of phone numbers. Think of all the 1-800 numbers that are taken up by that. 1-866, 188. There is concern that we might run out of numbers eventually with so many people having cell phones and landlines and fax numbers.
Well, aren't there only like 300 million people in the United States?
But think of how many people have businesses, business phones. How many businesses?
All you have to do is add another digit on, and then you add. Then now you have 72 billion instead of 7 billion.
Or they could start adding on like letters.
Probably not letters, but I think, in the future, like this is way down the line. We don't have to worry about this. But way down the line, they may end up adding another digit that you have like a state number.
Then now you have like 10 times what you were set to.
Yeah, you would have 10 times more, which instead of 7 billion, you'd have 72 billion. Just adding one digit makes a huge difference. So like you could have like a state number, like Wisconsin, you dial 2 to get to. Kind of like how you have country codes, that you could have like a state code. But that's not anything we need to worry about. But it is something to think about when you see a number like that. It's a big number, but you think about how many people have phone numbers nowadays. And you think of Brookfield Academy itself. Just the school itself has a whole bunch of phone numbers associated with it. Like when you call the upper school, you can call a whole bunch of different people at the upper school.
My brother one time called my mom and her.
Our next thing we're going to talk about are permutations. Permutations really are a subset of our counting theorem. It's just a more specific group of a counting theorem. So our first thing is an example of a permutation. I'm already going to get this in your head. When you think the word permutation, think order matters. Because on Monday we're going to learn something called combination, where order does not matter. So when you read the word permutation, you need to think order matters. And I'll talk about what order matters in this case. So you are giving a speech on books, and you want to start with some jokes. Always a good idea to start your speech with 4 different jokes. Always a good idea if you're ever giving a speech. All right, so we have 4 jokes we're going to tell. First joke that we can choose from. We don't know the order yet. We're going to choose that in a second. So the first joke we can choose from is, I like to play chess with old men in the park, although it's hard to find 32 of them. That is Emo Phillips. If you never saw him, he is funny. If a word in the dictionary was misspelled, how would you know that? That was Stephen Wright. A bit of advice, never read a pop-up book about giraffes. That's Jerry Seinfeld. And a few decades ago, we had Johnny Cash, Bob Hope, Steve Jobs. Now we have no cash, no hope, and no jobs. Please don't let Kevin Bacon die. That was Bill Murray. All right, we are telling these jokes. And I want to tell them in a specific order. I don't want to ever repeat the same joke. I'm not going to keep giving the same joke 4 times. That would be dumb. Not to mention I'm already giving 4 jokes. I don't know why I'm doing that either. So we're going to pick one of each jokes. So let's just set this up. So I need to find a joke to tell first. The first joke I'm going to tell. How many jokes do I have to pull from to tell on my first joke? We have 4. I already told you, we have 4 jokes. I'm going to pick one of them. So our first joke, we have 4 different jokes we could pull from. How many jokes do I have left to tell on my second joke? We're going to have 3. You lost a joke. You already told the joke. There's only 3 left to choose from. Our third joke, we lost a joke. We only have 2 left. Our fourth joke, we only have 1 left. And just remember, this is our fundamental counting theorem. I am pulling one joke, one joke, one joke, one joke. I have 4 groups of jokes where I'm pulling one joke from. So we're going to do 4 times 3 times 2 times 1. In other words, we have 4 factorial. That's important to permutations. That fact that we do have a factorial is going to be important to our permutations. In other words, we're going to have 4 times 3 times, which is 12, times 2, which is 24. All right, so if I have 4 jokes, and I'm going to tell all 4 jokes, I'm going to have a 4 factorial as my answer. What if I would just tell 2 jokes? How many possible ways are there to tell just 2 jokes? Yeah.
1 factorial.
Not 1 factorial. Don't worry about the factorial. Just look up here. What if I just told the first and second joke and I stopped there?
You have 2 combinations.
What if I just stopped at the second joke?
Oh, 12 jokes.
We're going to have 12 jokes. So if I stop at telling 2 jokes, first one I have 4 to choose from, second one I have 3 to tell from, that's 12. I don't have to tell all of the jokes. I just have jokes and I'm going to pull 2. Well, we are going to use something like 4 factorial, but notice it's 4 factorial, but it stops at 3. Or if I tell 3 jokes, I have 4 factorial, but it stops at my 3rd joke. So permutations are going to be a way for us to say, I don't want to tell all of the jokes. I want to know where I stop. I have 4 jokes, I'm going to choose 2 of them, or I'm going to choose 1 of them. That's going to be called a permutation. A permutation is going to be a way for me to pick a whole list of things and say, I want to do 4 of these. I want to tell 4 of these jokes. I want to tell 2 of these jokes. Now, a permutation is an ordered arrangement of items that occurs when no item is used more than once. In this case, each joke is only told once. The order of the arrangement makes a difference. The order in which you tell these jokes are told makes a difference in terms of how they are received. So order matters. Once again, permutation leads to order. Order matters. When you have a permutation of items, if you have a permutation of n things, I got 4 jokes. Take an r at a time. I'm going to tell 4 of them. I'm going to tell 2 of them. So this r is how many of the jokes I'm going to tell. The notation is permutation n pick r. Permutation is n pick r, represents the number of permutations r taken from n items. And here is our equation. I am going to note your biggest number is always going to be your n. So if you ever forget what's going on, your biggest number has to come first, which means your biggest number is going to be on top and it's going to come first. So biggest number is always going to be your n. You can't have 4 jokes and tell 5 jokes. It doesn't make any sense. I only have 4 jokes. So 4 needs to be my biggest number, or at least equal to how many I'm telling. All right, let's do a couple examples. You are a coach of a Little League team that has 13 players. You need to choose a batting order having 9 players. Now in baseball, batting order matters. If you've never played, it absolutely matters. Who starts, who's second, who's third. Order matters. So in this case, order does matter, so it's going to be a permutation. I did write order does matter, permutation. How many batting orders can you form? So like I said, it's going to be a permutation. Our n value is the pool of things I can choose from. Up there is 4 jokes. Here I have 13 players I can choose from. Our r value is how many am I picking? Well, I'm picking 9 of them for the batting order. So setting this up, since order matters, we're going to use a permutation. And we're doing 13, and we're picking 9 of them. Well, the formula for this is going to be 13 factorial divided by 13 minus 9, and the factorial comes afterwards. That's going to give us 13 factorial divided by 4 factorial. This one isn't nice to shortcut, but you should recognize where you can stop doing your multiplications. So I'm going to write it all out, but eventually you're going to get to the state where you can just stop multiplying. So we should do 13 times 12. times 11 times 10 times 9 times 8 times 7 times 6 times 5 times, here's where I stop. I'm going to put 4 factorial. And that's because we have 4 factorial on the bottom. So we're always going to look at our bottom to tell us when to stop doing the multiplications. So in my calculator, I should know that this is 4, so I'm going to stop at 5. It makes your life a little easier when you realize that I'm going to cross out this 4 factorial. So in our calculator, we should type 13 times 12 times 11 times 10 times 9 times 8 times 7 times 6 times 5. And we're going to come up with a really big number. Let's go ahead and plug that in.
Wait, is there
Anyone get this value? Labib?
259,400,000.
Oop. I lost it. 259 million. Yep.
459,200.
Yep.
All right. So there's a lot of ways with 13 kids I can set up a batting order. All right, our next one, you don't have this information, and I want you to put it in, maybe underneath it. I want you to realize that order definitely matters when you pick these particular 4 officers. Because sometimes officers' order doesn't matter. Maybe they're all the same officer. Maybe I'm picking 4 officers and they're all secretaries. Then you don't care which one you get. It's secretary 1, secretary 2, secretary 3, then order wouldn't matter. But this definitely matters. If I am picking president, vice president, treasurer, and secretary, you're not happy if you just randomly get selected one. Like you won for president and also I'm like, well, you get secretary because you randomly assigned it. That's not the same as you being president. So order definitely matters. So we're picking 4 officers are to be elected from a group of 12 people. And no person can hold more than 1 office. How many different outcomes are there? So we know order matters. We have a pool of 12 people, so my n is 12. And then we are picking 4 people out of there. This one's going to be an easier one to do because we're going to notice this is going to equal 12 factorial, but we are actually over 12 minus 4 factorial. I'm going to note that since we're 12 over 8 factorial, I really just have to do 12 times 11 times 10 times 9. I can stop at 8 because my 8s are going to cancel out. For notes purposes, let's write down what I'm talking about. So we have 12 times 11 times 10 times 9 times 8 factorial. All over 8 factorial. My 8s would cancel out, so all I have to do is 12 times 11 times 10 times 9. And who's got that total for me? Yeah. 11,880. Yay, nay? Good, that's what I got. All right, so today, it doesn't really matter, but it's going to matter on Monday. Start thinking about order. Does order matter? Why does order matter in these problems? I'll give you an example where order doesn't matter. If I'm putting if I have 5 ingredients and I'm choosing 3 of them to put into a smoothie, I don't care what order I add them in, order would not matter. And we'll get into that on Monday. But today, everything's order is going to matter. All right,